The first speaker is Shinji Hirano from Wits, and he's going to talk about random geometry approach to TTbar-deformed conformal field theory. So Shinji, please start.
Okay, thank you for giving me the opportunity to give my talk. And so my talk is going to be based on the works in collaboration with Masaki Shigemori at Nagoya University, YITP, Queen Mary, and Tatsuki Nakajima at Nagoya University. Okay, so so I organized my talk into 4 parts. In the first part, I first define what the TTbar-deformed conformal field theory is, and then I introduce an approach to TTbar-deformed theory that is called the random geometry approach. And then in the second part, I will apply this random geometry approach to the computation of correlation functions of the TTbar-deformed theory. And in the third part, I try to put forward the idea that there are two ways to view the TTbar-deformed CFT. And then in the last part, I will try to discuss the gravity dual of the TTbar-deformed CFT. Okay, so now I start with the motivation, and then I start with the conventional Wilsonian view of quantum field theory. This is for the purpose of giving a rough idea about what kind of field theory the TTbar-deformed conformal field theory is. Okay, so this is well-known possible patterns of the renormalization group flows for the quantum field theory. And so what is plotted is the RG flows in space of couplings. And there are 3 patterns people thought about, but for the conventional unitary local quantum field theory, the RG flow is known to have this RG flow. So it starts from UV fixed point, and then it flows to infrared. And then this lambda 1 would be the relevant coupling, because as you flow to the infrared, it increases. And then lambda 2 would be irrelevant coupling, because it will decrease as you flow to the infrared. And then if the theory is non-unitary, some other RG flow can be possible. And then, for example, Klebanov et al. Recently found that there is a non-unitary theory which shows this cyclic flow. And I don't know any example of this ergodic flow. But but the left one, this is the conventional quantum field theory. Right. So now, the theme of my talk is the TTbar-deformed conformal field theory. And then, so this is the action for the TTbar-deformed theory. So this is the action. And then you start with some quantum field theory, and then you deform this theory by this TTbar operator in quotation. And then this operator is irrelevant because the dimension of this operator is 2D, which is greater than D, and therefore it's irrelevant. And the coupling constant for the TTbar deformation has the length to the D's dimension.
Sorry, question here. How do you define the TTbar operator in higher dimensions?
Yes, so it's given by, it's similar to 2D case, and then it's believed to be a Tij minus 1 over D minus 1, and then trace T squared.
Okay.
So it's quite similar to the 2D case. But of course, people haven't really studied a higher dimensional case very well. Okay, so now I want to make the point that, so now this is the action for the TTbar-deformed theory. And clearly in the infrared effective theory is the undeformed quantum field theory. So in this figure, so let's suppose we start from conformal field theory, then we would be starting from this infrared fixed point, and then it flows back to UV somehow. But the thing is that we know that TTbar-deformed theory will not flow to the UV fixed point. So we don't know where it goes. So in that sense, this is a new and unconventional type of quantum field theory, and therefore it's very interesting to study. And the coupling being irrelevant means that it's power counting non-renormalizable. Nonetheless, this theory is quite controllable, and it's not even perhaps cut off effective theory. And it's marginally well behaved. And moreover, it's integrable. So we can solve this, and therefore we don't suffer from these UV divergences typical for the irrelevant operators. And so this is rather very special theory in that sense. Okay, so in this talk, I'm not the integrability guy, and so I will not emphasize the integrability of this theory, but rather I approach this theory from a different viewpoint. Right, so this is a rather interesting irrelevant deformation, but also this is actually kind of universal and model independent, because so we can start from any local quantum field theory, and as long as, and then it has a stress tensor, then we can always do this deformation. And so maybe it means that there's a wide range of applicability of this TTbar deformation. And so now I want to make another point for my motivation. And first, so you know that the stress tensor is a response to a change of the metric. So you start from some theory living on some space endowed with this metric, and then you deform the space like this. Then what happens is that the action will be deformed by this, by definition of the stress tensor. Sorry. So so there's a certain sense in which the TTbar deformation is geometric because it's a deformation by stress tensor, and therefore, and even it's irrelevant, and therefore it may provide a new perspective on short distance physics. Well, it may tell us something about the short distance geometry of the space in which this TTbar-deformed field theory lives. So that's another motivation. So because I'm a string theorist and I'm greatly interested in the short distance physics in space-time, and so TTbar is kind of like toy model to study short distance physics. That's my take on this TTbar. And then my main field of research has been gauge gravity duality or ADS-CFT. And so I have naturally a motivation from the viewpoint of ADS-CFT. So simply put, so I am interested in finding the gravity dual of the TTbar-deformed CFT or TTbar-deformed ADS. And what you see in this slide is so this is the geometry created by some bunch of D branes. So or a bunch of M branes. And so you have, so here, this is supposed to be an asymptotic flat region. And then as you approach to the bunch of D branes, the space is warped like this. And then conventional view is that, so H is the harmonic function of this gravitational solution for the D brane geometry. And then, so what we study in ADS-CFT is this near horizon region. So this is the region below this. And then the warp factor becomes this. And then we know that, so this is the asymptotically ADS boundary, and then we can go down to the bulk of ADS space. And this is the near horizon region. And then in connection to quantum field theory, we can think of going down as the RG flow by some relevant operator from the UV fixed point to the infrared fixed point. And now in 1999, people actually proposed how we might be able to go away from the near horizon limit to well, it's an attempt to find the holography in asymptotically flat space-time. And then the key is that, so when you go from asymptotically flat d-brane space-time to near horizon limit, you drop this constant mu. So mu is a constant. And then as it turns out, this corresponds to the deformation by delta equal to d, irrelevant operator. So, it's done by Gupsa and Hashimoto, and also Klebanov et al. And then, so by doing this irrelevant deformation, you would be flowing back to far ultraviolet to asymptotically flat region of space-time. And so delta equal to d is, of course, the same dimension as TT bar, but it's a slightly different, in fact. So this is actually single trace operator. So in the context of TT bar, like Kutasoff, Itaki, Gibbon has this single trace operator TT bar deformation, and they have this gravity dual, which is asymptotically flat. But the TT bar people often discuss is actually double trace deformation. And so it doesn't quite flow the space-time geometry to the asymptotically flat region. So we have to understand what this is in the context of ADS-CFT. And of course, the well-known proposal is done by these people. And one interpretation is you put the cutoff near the ADS boundary that corresponds to this TT bar deformation. But I'll come back to this in the last part of my talk. So these are the motivations. Okay, so let me start part one, the random geometry approach. So this was proposed by John Carey. And first, I have to make a definition of TT bar more precise. So the idea is, so you start from some TT bar deformed theory, and I call it T mu, and then you can deform further by small amount, delta mu, and this is the precise form of TT bar operator, and then you get further deformed theory, I call mu plus delta mu. And so idea is you start from T0 theory, which I take as 2D conformal field theory. And then you deform it little by little, and then you iterate this deformation process. So then in the end, you get the TT bar deformed theory with finite coupling mu. And why would I have to do this? You might wonder, why can I just start from this? The reason is the following. So first, what people call TT bar is this one. So it's TT bar minus theta squared, and theta is the trace of the stress tensor, and it's given by a determinant T. So in the conformal field theory case, you don't have trace, and so it's just TT bar. But generically, you have this contribution. And then the reason why I define TT bar in this way is that, so this stress tensor appearing in this deformation is that of T mu theory rather than that of conformal field theory or T naught theory. And so it's actually more complicated than you might think. So we cannot just put the TT bar here and then think of this as a well-defined theory, but we have to do this process of, we have to deal with changing stress tensor. So that's why we have to do it infinitesimally, step by step. Okay. Right. Okay, so now this random geometry approach is to use the trick, well-known trick by Hubbard and Stratonovich, that is, so TT bar is clearly a bilinear operator, but we can linearize it by introducing auxiliary field. So this is the TT bar deformation. And now we introduce this auxiliary metric H. And then we write it as this, and then we integrate over this auxiliary field, we go back to this TT bar. But so as you can see, we linearize it, and so now it's easier to deal with this deformation. And moreover, the stress tensor, as I emphasized, is a response to a small change of the background metric. And so this can be reinterpreted as the change of the background metric by small amount h. So this is geometrizing TTbar-deformation. So to summarize what I just said, so this is this is the action for the T mu plus delta mu theory. So to get this, we start from the action for the T mu theory, but then we deform the metric of the space where this T mu theory lives, and then we Gaussian average over H. So that way we can get this further deformed action for the T mu plus delta mu theory. Okay, so now we can easily generalize this argument for more generic physical observables. So action is roughly, so I just mentioned about free energy, but now I can generalize this physical observables. So to get physical observables of the T mu plus delta mu theory, we start with the observable of the T mu theory on this deformed metric G plus H, and then we Gaussian average over this H, and then we get the physical observable for the T mu plus delta mu theory. And then because I'm considering a small delta mu, a small infinitesimal transformation, and it's like h bar, so small h bar, and so the h integrals are dominated by the saddle point. And then you get also Gaussian fluctuations about it. So this h integral is approximated, very well approximated by a saddle point plus Gaussian fluctuations about it. Right. And one more comment is that if I go back to this expression, the saddle point of H is in fact this. And so this gives you an intuition what H is. So H is basically, you can identify it as stress tensor. So this is intuition you should have in mind. So now I want to demonstrate how this method works. And so I take some example. So I consider this well-known example. So let's consider the T mu theory on a cylinder S1 close interval I. So this T mu theory lives on this. And then it's well known that the energy spectrum of this theory is given by this formula. And it is found by these people, and I call it the SZ formula. So as you take mu to 0, you recover the conformal field theory energy spectrum, which is some constant divided by R. So this is the deformation. Sorry. Okay. So for the simplicity of the argument, I focus on the case without momentum flow. That is, so there could be momentum flow in the horizontal direction, but I consider the case where we don't have any momentum flow. And what it means is that I switch off the off-diagonal component of the stress tensor. And as I mentioned in the previous slide, so that means that I switch off the off-diagonal part of this auxiliary metric H. And then this Gaussian Harvard-Stratton-Rich action becomes this, given by diagonal components of the metric. Right, okay. So now, so as I said, so introducing H will deform the metric of the space. And so the metric of the space is just flat. And I consider the Lorentzian case. And so what deformation does is just the rescaling of this diagonal component of the metric. Or in other words, so this it's a rescaling of the coordinates t and x, or t and radius r. Right. So to get the energy spectrum on the for the T mu plus delta mu theory, I use this. I use the algorithm I explained. So I start with energy spectrum of the T mu theory, and then I put this on a deformed space. In this case, just the deformed space is just the rescaling of this radius and time, and then I have to do the Gaussian average over it, and then I should get this. And because because this is well approximated by the saddle point, I focus on the exponent of this expression. So the exponent of this expression on the left-hand side is this E mu, the energy for the mu plus T mu plus delta mu theory. And on the right-hand side, this is what we have. And then because H is quadratic, you can easily find the saddle point, and then you get this saddle point. And then in the end, what you get from this saddle point analysis is this partial differential equation. And this is the well-known implicit Burger's equation. And then we know the solution, which is actually the SZ formula with the initial condition that conformal field theory energy is given by this. So this is how we can use this random geometry approach to solve some of the problems in the TTbar-deformed theory. Okay. Now, so there are another way. I used a partial differential equation to solve the problem, but I can do iteration order by order in mu. So as I mentioned before, so to get the finite TTbar coupling mu, one way to do it is to iterate this infinitesimal transformation. So, but when I derived this SC formula, I used a trick because I could get a partial differential equation. But I can just do a more straightforward order by order iteration too. But to do that, I make a note that actually there is an alternative view of the TTbar-deformed CFT, which is so TTbar-deformed CFT can be thought of as undeformed CFT on deformed geometry. I will come back to this in part 3. But what it means is that in this context, so the energy spectrum can be written in this way. So it looks like a conformal field theory energy on a cylinder of a circle radius r. But so this r is now deformed by mu. So this is like a CFT energy, but with the deformed radius. And given this, then what I should do is, so this is the ith iteration, and then I want to go to the I+1 iteration by Hubbard-Stratonovich transformation. So I have this Hubbard-Stratonovich Gaussian part, and then I have the rescaling of the energy corresponding to deformation of the metric. So in this case, because it's just 1 over r and there's time t, and so we have this. And then because it's a step-by-step iteration and it's a small step, and so I can approximate this by this. So once again, I solve a saddle point equation, and then in the continuum limit, I get this equation. And in fact, the solution to this equation is precisely the SZ formula. So I derived a SZ formula in a different way. And then moreover, you can read off the deformation of the radius, which is given by this. So this viewpoint, I will come back later. Okay, so this is the review of the random geometry approach. And I want to move on to part 2. So maybe, do you have any questions?
Yes. Could you go back to the previous slide?
Yes.
So this is the case when you assume there's no momentum. So, and then the deformation is basically diagonal. So what happens
Yes.
if you have momentum?
I haven't actually calculated it, but well, well, I should get well SC formula with the momentum, but if your question is how exactly I should do that, I don't know. Okay, yeah, well, you have to simply add this h11 h22 minus h12 squared, and then I have to involve h12. Right. So that's what I should do. Does that answer your question?
Because once you have, so basically, in a case, if you neglect the diagonal component, you just need to rescale the radius and the length of the cylinder. But once you turn on the off diagonal component, I guess,
Yes.
I mean,
Yes.
the change of coordinate is more complicated somehow.
Yes. Yes, that's right.
So I want to see how that should work.
Okay. So then I have to confess that I haven't worked out in that case, but it has to work out. So yeah, at the moment, what I can say is I haven't really worked it out.
Thanks.
Okay, sorry. Yeah, sorry about it.
No problem.
Okay. Right. So now I move on to the computation of correlators. So in the original Cardy's paper on this random geometry method, he never used random geometry approach to compute the correlators. So we have to generalize it to the computation of correlators. And first, I note that so the 2D metric can be decomposed generically into this form. So you have a diffeomorphism part, and then you have Weil plus conformal transformation part. So this is the standard decomposition of the metric. So then to compute the deformed correlator, okay, so I focus on the case with infinitesimal delta mu, and I start from CFT. So this is the deformed correlator. This is the deformed correlator, and then the recipe is to start with conformal field theory correlator, and then so because this deformation of the metric corresponds to the first diffeo and some Weil transformation, and so I have this. So I mentioned that. So if I focus on leading logarithmic corrections to the deformation, then I can actually ignore this Weil factor. And so from now on, I ignore this phi. And then what I have for this metric deformation is only a coordinate transformation by alpha. So now the CFT coordinate is living on this coordinate. And then because this is the primary field, and so coordinate transformation induces a Jacobian for the primary operators. And so I have to take care of this part. And then, so the Hubbard-Stratovic action becomes, in terms of alpha, this. And so what I should do now is to integrate over alpha to get the deformed correlators. Okay.
Sorry,
so now,
one question just to understand.
yes.
So here you start with CFT and then you just do a very tiny deformation, right?
Right.
And previously you were starting at any point of the flow, and then on top of that, you do a very small deformation.
Right.
So why don't you do that here?
Yes, I will do it later, but I think, right, as the simplest illustration, I just try to first show the first order correction. Then I will generalize this to higher order. Then, yeah, so I will start from some T mu theory.
Okay, thanks.
Okay, right. So for this, once again, so the alpha integral is dominated by a saddle point. And so the you can find a saddle point, and it's this expression. And then you plug this in back to the expression. Then this is the saddle point approximation of the alpha integral. Right. So you have conformal field theory correlator, and then you get the deformation, this delta mu. Right. So this is the expression for the first order correction. But to make it more explicit, I consider a 2-point function as an example. And then if you consider 2-point function, this whole expression becomes this. So this is the correlator in the T delta mu theory. And this precisely agrees with the result found by these people. Okay. So now I do what Yunfen suggested, so to find the higher order corrections. So now, so instead of starting from CFT, I start from some T mu theory, and then I repeat the same process. So now this is the correlator of the T mu theory, and then I want to get the correlator for T mu plus delta mu theory. But okay, so first, so this is the saddle point action. And then as it turns out, I need to include Gaussian fluctuations about it. And so now so far, Gaussian fluctuations could be ignored because it didn't contribute at all. But from here, I need actually to include Gaussian fluctuations about the saddle point of this alpha integral. And so I included it. And then similar to the case of this energy spectrum, I can get the partial differential equation. And this is the partial differential equation for the deformed correlator, or the correlator of the T mu theory.
So
and,
how did you derive that partial differential equation?
It's actually exactly, I do exactly the same thing like this one. I had actually some the correlator for the T mu plus delta mu theory, and then I had the whole expression, and then I just, because delta mu is infinitesimally small, and so I just, you can derive this partial differential equation, and it's exactly the same process for the correlator. Right.
Okay.
Yeah. Okay. So then, so this looks a little bit complicated, but it has more simple form. And so you can massage it, and then you get this expression. Well, it's still, so this is kind of, this is a diffusion equation, basically. So you have some time. Well, so this is the deformation parameter mu, and then you have this kind of Laplacian. And so it takes the form of diffusion equation. Right, so this is, and then as a concrete example, once again, you can actually solve this in the case of 2-point functions, and then you Fourier transform it, and then well, the easy way, I guess the way to solve it is actually to Fourier transform it to a momentum space, and then you can solve this differential equation. And in fact, the solution is given by this expression. And this agrees with the expression found by Cardi in other methods. And importantly, this is an all-order expression. And so, well, basically, TTbar-deformation, what it does is it gives anomalous dimension. So because delta is now kind of shifted by this, but it's kind of space dependent or momentum dependent. So it gives the anomalous dimension of space dependent type. So that is the result for matter correlators.
Right. About this shift of dimension, so is it somehow consistent with the deformed spectrum? I was thinking about this state operator correspondence, and then the dimension of the operator should correspond somehow to the spectrum. on the cylinder, at least in the CFT.
Yeah.
So now,
Yes.
okay, now it's shifted like a log.
Ah, I see. I see your point.
Yeah.
Right. So if you kind of try to rewrite this energy spectrum in terms of anomalous dimension, then does it agree with this expression? That's your question, right?
Yeah.
Um, well, okay, good point. I haven't thought about it. But I don't think it agrees. So first, this is the space here is R2. Okay, so then you say I should map it to a cylinder by conformal transformation.
But probably it's not conformal theory anymore. So
Right, yeah, that's why. Yeah, I
cannot do
cannot
that.
exploit conformal transformation. Well, I think it's a very good point, and there must be some relation, but
Yeah.
I don't know how exactly I can relate these two.
Mhm.
Right,
Okay.
but that's a very good point. Right. Okay. So now, okay.
Sorry,
So
I have a
this
question.
is the end. Yes.
Did you explain the meaning of epsilon?
Epsilon is a cutoff. Sorry. Yes, epsilon. I have to introduce a cutoff because I have this green function. But you can renormalize it by a wave function renormalization. So you can get, so this is the cutoff you have to introduce for the computation, but then you can renormalize it away. Right, so this is like a UV cutoff.
Okay, yeah.
Right, so if the expression, the final expression depends on cutoff, then this is a cutoff effective theory, but you can actually renormalize it by wave function renormalization of these operators.
Another question, just out of your curiosity, have you tried to play this formula with some massive free theory, say free boson? I mean, not the CFT.
No, I haven't done the free field computation. So
Okay.
are you suggesting I take a free field and then I do just free field computation to get this one?
Yeah,
I
I'm just
haven't.
curious. Yeah, just
No,
curious.
I don't know. Yeah, I haven't done it. No, sorry.
Okay. Thanks.
Okay. Right. So now I want to move on to the stress tensor correlators. So far, it was just some primary field correlators, but I want to generalize this method to the computation of the stress tensor correlators. Right. So the idea here is that so it's related to conformal anomaly. So first, I point out the fact that so in the past integral formulation, conformal field theory stress tensor correlators can be calculated from the conformal anomaly action by taking the variation of the conformal anomaly action. So therefore, if I want to use this random geometry approach, I should start from conformal anomaly action and then do the random geometry trick to get the deformed conformal anomaly action. So that's the idea. And to do that, I have to generalize this method to a curved space because I want to take the variation of the action with respect to metric. Okay, so, but the idea is simple. So you start from a conformal anomaly action, which is given by this famous Polyakov-Liouville action. And then I do the same thing. So I put this on a deformed space, and then I average this over the deformed metric, and then I should get deformed conformal anomaly. And here, so once again, the metric H can be decomposed into this way. Right. So the idea is simple, but it's a bit technically tedious. But nonetheless, you can just compute. So in the end, what you get is this. So this is the Polyakov's famous conformal anomaly action, and then this is the deformation, and yeah, it takes this form, and the Gaussian fluctuation. Well, there's a bit about something about Gaussian fluctuation, but it can be renormalized to 0. So this is the expression. Right. Once you get this, then how do you compute stress tensor correlators? The way to do this is the following. So I want to consider stress tensors on R2. So then the metric G I should take is R2 metric, and then plus H. And in this case, this H is the source to the stress tensor. So in other words, if I have this metric for this expression, then by taking the variation of this action by this H, and then I get stress tensor correlators.
Sorry, may I have a question?
Yes.
Because in the previous slide, so you were saying first we consider the theory on curved spacetime.
Yes.
So then you have this conformal anomaly. Well, in the next slide, you are expanding Gij as delta Ij plus Hij. So it's like
Yes.
flat. So is there?
Not quite. So H is generic.
Okay, H is generic.
Yes, because I have to take the variation of H, and the H depends on the space.
Okay.
Right. Yeah. Right. So that's why I have to generalize this argument to the curved space. Right. So now the task is kind of straightforward. So once I get this, then I just take the variation. But in practice, it's kind of quite tedious. And then the practical way to do this is to go to the conformal gauge, just like you do for this Liouville action, the Polyakov action. So because when you go to the conformal gauge, you know that this becomes a free field theory, and locally it has the local expression. And a similar thing happens even for this horrific deformation. So once I go to the conformal gauge, it becomes actually a local expression. And I skip that process. So I just give you the answer. So once you do that, you get this whole bunch of results. And first, I make a comment that generally the stress tensor correlators has this delta function and derivative of delta function contributions, which is called contact terms. And I get this, but I'm dropping these delta function contributions. So first, 2-point function don't get first order correction, and the correction starts from second order, which is known by the work, which we know from the work by Krauss to Marlov. And then by this method, we can get the 3-point function, and it has this expression. And this was also found by these people, and it precisely agrees with this result. And then the 4-point function is a new result. And then what we have is these 4-point functions. These are the corrections. So if the theory is not TT-bar-deformed, first of all, for example, theta is 0 and it should be vanishing. And then there is no correlate between T and T-bar because they are just decoupled. But TT-bar makes theory non-holomorphic, and so everything starts coupling. So that's why you start seeing all these correlators, what you don't see in CFT. And so these are the expressions, and we could manage to compute this only to the first order. And the second point is, yes?
Why only to the first order? Your formula looked like non-perturbative.
No, it was actually first order delta mu.
Ah, I see. So,
yeah, to go to the higher order, perhaps we have to find a clever partial differential equation. This iteration seems formidable. It seems extremely complicated.
I see.
Okay.
So for this action, you only get the first order. That's why I
Yes.
see.
Yes.
Thanks.
Yes. Right. And so this is the expression, and I'm kind of running out of time. Okay. Right. And so the point to make is that so it was mostly power corrections, but then this one, from this one, we start getting this log collection. And okay. So another point I should make is that you can actually compute first order correction by a conformal perturbation theory. And we have done it, and we compare the result, and so this precisely agrees with this conformal perturbation computation. But the point here I wanted to make was that I wanted to use this geometric method of studying TTbar-deformed theory, and so I insisted on using this random geometry approach. Now,
by the way, you have 15 minutes because you started a little bit late.
Okay, I might have to skip the last part, but okay, let me, okay. So now I want to make another point. So given all these deformation to the correlators, you can read off the deformation to the operator OPE, the operator product expansion of the stress tensor. And there are a couple of deformations, but I focus on one particular one here. So I focus on this deformation to the OPE for this TT, and TT gives actually T bar and with this integral. So the reason why I single out this particular deformation of the OPE is that it shows something interesting. So it shows some non-locality. So in the standard quantum field theory, when you do the OPE of two operators, then it will be expanded by the local operators. But it seems that for the TTbar-deformed theory, you actually get some non-locality in the operator product expansion. So maybe this is a signature of the non-locality of the TTbar-deformed theory. And then you can check whether this is correct. And well, in fact, so I have the expression for this 4-point correlator. And then I just consider this regime in this correlator. So Z12 is small and Z34 is small. And I expand this for small Z12 and Z34. And then I can do the computation in the OPE. So I can do the OPE of this and the OPE of this, and then subsequently OPE of this. And then you can check that this precisely agrees with this expression for small Z12 and small Z34. And in fact, this log is the source for this log collection. And somewhat, so this log is linked to this non-locality of the OPE. Okay. And I don't show other deformations, but yeah, this is the most peculiar one. Okay, so now I have like 10 minutes, and okay, at least I believe I can finish part 3. So this is related to Yunfen Zhang's work, and they studied some kind of TTbar deformation of the quantum mechanics, and then they arrived at some interesting picture of this short distance physics. And this is related. And so first, I want to put forward the idea that there are two descriptions of the TT-deformed CFT. And so one is the TT-deformed CFT, but it's living on some space, which is equivalent to undeformed CFT on TT-deformed space. So precursor of this relation was had appeared in my demonstration of the energy spectrum computation. And so this random geometry approach makes it pretty clear that why this there is this two alternative descriptions of TT-deformed CFT. So from that saddle point analysis, you can get the explicit coordinate transformation from this undeformed space to TT-bar-deformed space. So here, Z is the coordinate on R2. And then this capital Z is the coordinate on this TT-bar-deformed space. And as it turns out, they are related by this transformation, and it involves this operator T-bar. So this is an operator or state-dependent coordinate transformation. And then, so this is a deformed stress tensor. And in fact, you can find the expression for the deformed stress tensor order by order. And it has to obey this equation. And loosely speaking, well, you anticipate from this relation that this deformed stress tensor is roughly given by this expression, because it's a coordinate transformation from little z to capital Z, and it's a stress tensor on dimension 2, and so it now lives on the deformed space, and then you get the Jacobian for the dimension 2 operator. But it's in quote unquote. Precise expression is this one, and it gives a sense of this quote unquote expression. So you can calculate this deformed stress tensor order by order by doing solving this equation. Okay, so that's another point.
Sorry, may I ask a question here?
Yes.
In this dynamical change of coordinates, this is not the familiar one which I see in the other literature, say in Takeo's paper.
I think that in Cardy's, one of Cardy's paper, actually, he has this expression.
So, okay, maybe some transformation is done. Well, okay, I should check it. Thanks.
So, this appeared in his paper on the computation of correlators.
Mm-hmm.
Of course, we express it in a slightly different way, and so it doesn't look familiar. But yeah, it is the same. Okay, am I? Okay, right. So now I move. Okay, I move. So now, given this, I want to prove the state-dependent TT-bar-deformed space. So it's operator dependent, or by operator state correspondence, it's state dependent as well. So to see, in my attempt to understand this TT-bar-deformed space, I consider this wave of the TT-bar-deformed coordinate. So I consider this wave on some primary state delta. And then you can actually do the computation, and this is the full expression. And I note that so the derivative of this satisfies this implicit Burger's equation. It's just a remark. And then, okay, whatever this expression is, so this, I plot it. So it's easier to understand in the plot. So the plot is, I'm plotting the modulus of this as a function of modulus z, as little z, and so then it looks like this. This is the function. This curve corresponds to this function, and I discussed two cases. I have to separate two cases. One is when the TT-bar-deformed coupling is negative, and the other is the TT-bar-deformed coupling is positive. And then this negative case is known to show some limiting temperature, which is the Hagedorn temperature. And in the positive mu case, it's known that the energy becomes complex at high energies. That's what you have seen in this SZ formula of the energy spectrum. Okay, so this is the curve, and okay, I tried to make it shorter. Okay, so first I observed that from this, there's minimal distance in the TT-bar-deformed space. For example, this is it's clearer in this case. So clearly there's a minimum. So this TTbar-deformed coordinate has the minimal distance for the negative case, and the positive for the positive mu case, I will explain later, but it has this minimum. I argue that it should be cut off here, and so this is the minimum for the minimal distance for the TTbar-deformed space for positive mu. Right. So as you see, the short distance is significantly altered in a state-dependent way. And of course, this is expected since the TTbar deformation is irrelevant and also it's geometric, right? So now I want to point, there's some sense in which we have UBIR mixing in this TTbar deformed theory. So for example, I can consider the insertion, the location of the insertion, operator insertion. So, okay, to explain it, so having this cat state means that you inserted the operator at the origin, and then having this bra state means that you have inserted the operator at infinity. And so z equals 0 is operator insertion point. And then, so this maps to this in this TTbar transformation. And then you see that as you increase delta, which means that you are going to the high energy. In fact, this coordinate z also increases. So the increase of coordinate is the large distance. And on the other hand, the increase of delta is like you are having high energy. So high energy corresponds to large distance, and so they are mixed up in this TTbar-deformed theory. Well, or you can see it from here too. As you increase delta, then the minimal distance increases, and so it's going to infrared as well. So there's some sense in which TTbar theory shows UV-IR mixing. Okay. So now I have like 5 minutes. Okay. So now I come to Yunfen's rod picture. Well, it's preliminary, and it's all even my tentative understanding, and so it may have to be revised. But this is what I think at the moment. So I first consider a positive mu, which is the case for the complex energy, and then you can calculate the wave of the stress tensor on this state, the delta. Then this is the expression you get. So, right, if there's no deformation, it was delta over z squared, and then there's a singularity at z equal to 0, corresponding to the fact that you have the operator insertion at the origin, corresponding to the cat state. But then it develops another singularity at this particular point I call z min. So this the value of z at which this vanishes I call z min. So I interpret this as that so there is some source for the stress tensor, and then you cannot really penetrate into this. That's how. So I claim that well, this region should be cut off. This region should be cut off, and then in the TTbar-deformed coordinate, it looks like this. And so this was the operator insertion point gets mapped to this circle, but then there is a bigger circle surrounding it, and it's this one. Oh. So I claim that, so this shaded region is like a 2D generalization of the rod picture Yunfen and Cardi Doyon found for the quantum mechanics. And right. And for the negative coupling, the claim was that you have a negative rod or a free space. That was the claim made by these papers, and I'll try to do this in 2D case. so unlike in the positive mu case, where this square root is always positive for negative mu, and so we have no reason to cut off the space, and so it covers entire region. So here, this region is not removed, but it's there, but I just color coded the space. So now, once again, the origin is mapped to this circle, and then this green region is mapped to this annular strip. And so this particular value of Z corresponds to this circle. And then, in fact, in the TT-bar-deformed space, there's no inside here. So this region is removed. And then this is the operator insertion point. And then instead of becoming bigger, it now becomes kind of smaller. And then I claim that this green annulus region is the negative rod or free space. So to understand it, if you put some other operator and try to approach this operator to this operator, then what will happen here is that it comes from here, and then it passes through. It passes through this operator, and then it goes back. And so it's like it's creating a free space or negative rod. And so that's the picture for this negative mu case. Right. So this is I think this is the end of the part 3, and I tried to explain what deformation was done to the short distance physics of the TT-bar-deformed theory. Okay. So Ryo, I think I'm out of time, right?
Yeah, that's right.
Okay. So I guess I'm not sure. So people may not be that much interested in ADS-CFT. Yeah, so I think I can finish it here. So I can skip to the last slide. So I had like 3 slides for ADS-CFT, but okay, let me skip. Yeah, I will finish it now. So future. What is the future of this work? So one thing I really want to understand is understanding the TT-bar-deformed theory from the viewpoint of CFT on TT-bar-deformed space. So I want to understand this short distance physics for the TT-bar-deformed theory. And another important point, I think, is this non-unitarity issue of the TT-bar-deformed theory. There is an indication that TT-bar-deformed theory is non-unitary in the following sense. So there is a paper who studied simplest TT-bar-deformed theory or some ON model with TT-bar deformation by a Kyoto group. And then what they found is that the trace of the stress tensor, the 2-point function of the trace of the stress tensor becomes negative at short distances. So at the large distances, it is positive, but as you go to the short distances below the TT-bar deformation scale, it becomes negative. So indicating that there's a negative norm developing at short distances, which is an indication of non-unitarity. And but I want to confirm this claim generically from the computation of stress tensor correlators. And then another point, maybe we can apply this TT-bar deformation to AGT relation. So AGT relates, for example, SU2 case. So SU2, sorry, N equal to SU2 Seiberg-Witten theory can be, well, it's equivalent to Liouville theory. And so if we apply this TT-bar deformation to Liouville, then something happens to the Liouville side, and then it must correspond to some physical phenomenon in the N equal to super QCD. So that's one interesting thing maybe I want to study. And finally, so I think even in the beginning of this TT-bar deformation, once this energy spectrum was found, people saw that there is a complex energy developed at high energies for this positive coupling. And then there's a Hagedorn limiting temperature appearing in the case of negative coupling. But people didn't, I think we haven't really understood what it exactly means, and whether the complex energy should be allowed, etc. And that's something maybe the gravity dual description might help us to understand it. Okay, so let me finish my talk here. And I see some the question in the chat. Oh no.
No. Anyway, thank you very much. If you have any more questions, please unmute yourself.
So I have just one comment on the hard-rod picture. So in the quantum mechanics model, what becomes the hard rod is we are more in the excitation, how to say, this particle picture. So each state has certain particles, and each particle becomes finite size. And here in your case is more like the operator itself becomes finite. So it's slightly different, but it's intriguing.
Right. Yes, I completely agree, because it's conformal field theory, and so we don't have particles. And so instead we have operator. And so, yeah, that's why analogy is, so operator is analogous to a particle in quantum mechanics.
So is there any physical meaning for this minimum value of this Z, this capital Z?
Physical meaning, the one thing, of course, is that it's by dimensional analysis, it has to be square root mu. And so the presence of this length squared scale, presence of the length scale because of TTbar-deformation will change the physics below it, below this scale. So of course the most rough picture is as soon as you introduce this new scale, then something happens at this particular scale. But if you ask me more, so then there's a details to it, like it depends on the state. That is, it depends on the dimension of the operator. And what does that mean? Right. So one, I don't have clear. Well, I don't really have a good answer to physical meaning of this particular scale, but rather I wanted to discuss the implication of it. So that's why I brought up this UV-IR mixing.
Yeah.
Yeah, but no, I don't have understanding, but yeah, that's the kind of thing I want to understand to really understand this TTbar-deformed theory.
I see. Thanks.
Yeah.
Actually, I have some questions. The first one is about this CFT on the TTbar-deformed space. In this picture, you say this local operator is mapped to some operator on this ring or this circle. But then this is true for all operators, like or at origin or at infinity or at any point.
Yeah, infinity maps to infinity.
How about finite?
So I think it's true for any position, because you can always make a translation from one point to the origin, and I consider this a generic feature. Yeah.
Yes. Yeah. So each local operator is now mapped to some kind of non-local operator.
Right. Yes. Yes.
Do you know what kind of if other kind of operator exists? For instance, there's a local operator on this TTbar-deformed space, or if you start from non-local operator on the original theory, then it's even more non-local on the TTbar-deformed.
Right. Okay. First, I think because of the short distance modification, to the TTbar-deformed space. So in the TTbar-deformed space, there shouldn't be a local operator. So it's always some kind of non-local operator. And so I believe this picture is quite generic. And then if I have some non-local, if I consider some non-local loop operator in CFT, well, I suppose, yes, it will become, well, in the first place, it was non-local, and then it will be non-local, but I'm not sure what exact, wait, I guess that, for example, so if you have some loop operator in CFT, then it cannot shrink to a certain size, right? So I don't think you can shrink it all the way on the TTbar-deformed space. So that's the kind of additional locality, manifestation of additional locality in the TTbar-deformed.
Okay. The another thing is some kind of physical institution. In particular, you said it's a UVIR mixing, but
Yes.
in my case, in my understanding, it's a bit different. You start from a theory and then modify the UV description a little bit. Then if you want to try to describe the physics in the UV deformed theory, you somehow need to a little bit scrabble the short distance behavior. That's your interpretation of the random matrix picture. Then you have to know the size of this scrabbling. Then this scrabbling is precisely this minimal distance. This distance of scrabbling also depends on the operator dimension. Is it I don't know, right way to think?
Yeah. Okay. Yes. Right. You kind of scrabble it, and so it's this kind of this picture. Yes, but I think no, I am okay. I think what I said is very similar to what you said, and so
no. I mean, in this picture, it's not really UV-IR mixing. You just have to scrabble. I mean, everything is about UV, but the distance. I mean, just the size of the scrabbling distance changes.
Yes. So, but so that size is determined by this kind of UV-IR relation.
Yeah, kind of.
I think that's my claim. So as you add a more higher energy state, then the size of this scrabbling has to become large. So it's kind of like infrared. So UV is now translated to IR.
Yeah. Okay. Any other questions? If not, let's thank the speaker again. And I stop recording.